Okay, hi everyone. So today we'll be looking at kinematics. So kinematics in uh, one dimension. So there's a few things that we are going to look at. So we'll look at examples. So remember last time we spoke about vectors and scalars, and we said we have something called a number, which is a mathematical object. Then we have a scalar, and we had a vector. Okay, so today we are studying examples of these. So we are studying, say for example, for a scalar we'll study something called distance, or at least introduce it, time, and then the equivalent for a vector. When we have distance, we have displacement for a vector. Okay, and then the equivalent, there's no equivalent for time, but we also have something called acceleration. um, and yeah, so velocity, which corresponds to speed when we go to scalars. So here we have speed, and there's many other examples. Maybe let's just mention them, but we're not going to study them in this section. So for scalars we also have mass, we have temperature, we have volume, we have area, of course, and so on. So anything that just has a number and a unit, so it doesn't have direction. And then over here we can speak about pressure difference. So pressure uh, differences, actually no, so just scrape that. Yeah, so there are other examples of vectors. Okay, so let's stop there. So for today we are interested in studying distance, time, speed, displacement, acceleration, and velocity. Okay, so let's start with distance. So distance, there are different symbols that we use for distance. Yeah, so for example, when we speak of gravitational problems where a body is falling or is being thrown up, we normally speak of a height and we use h. So in this case we use height. Normally people will use h to represent this, whereas if you have, say for example, a car moving along a road or in the x direction, for this we normally have distance, which we use s. Sometimes people use d for this, and distance, d, or height, or s, or whatever symbol you use, is measured in meters. Okay, so the SI unit is meters, and we just write the symbol m, so that's the unit. And then the formula, well, before we speak of the formula, we also have time. So we also have time, and time is normally by a clock or an equivalent, and we measure time in seconds, so that's the SI unit. Sometimes it can be given in other units like minutes or hours, and you have to convert these into seconds if you are working with SI units or any problem that we have. So anytime we write down an equation, so say for example we write S is equals to Vt, in these equations you always work with SI units. So make sure that you convert everything to SI units before you plug them in. Before you plug in the value. So for example, say a car is moving at 5 kilometers per hour, and okay, 5 is a bad number. Let's just change 5. Okay, let's choose a clever number. So let's say we have 3.6 kilometers per hour, and the car travels for say 2 seconds. Okay, and we want to know what distance it covers. You can see that here there's no match, so the time is in seconds and the speed or the velocity is given in kilometers per hour, so we need to convert the kilometers per hour to SI units, and we know that to go from kilometers per hour to meters per second, we just divide by so divide by 3.6, then you will get that the car goes at 1 meter per second. And then it's very easy to find the distance S. Do not confuse also, most people would confuse these two. This S is a unit for time, it's in seconds, and this S is for distance. So it's one of the examples of scalars. They are not the same thing. So in this case, then we would get that S is equals to Vt, and V is just 1, and time is 2. So the car just covers 2 meters. Okay, in 1 second, and that's the distance that it covers. So be very careful with the units. So now we have spoken about time, and we just briefly spoke about distance. So now we are ready to so let's just tick. We've spoken about distance, we've spoken about time. Now we are interested in speed. So let's look at speed. So what is speed by definition? So speed is the rate of change in distance. Okay, so how quickly we change our distance, and rate means per unit time. So then speed normally is given by a v. So then our v is equals to, it's the rate of change in distance. So that means I have distance over time. And normally people would then put some deltas to show that this is change. And the units for distance, if I can just remind you, was meters. The unit for time was second. So meters over second is just meters per second. Okay, so sometimes we use meters per second like that because that's just easy when you are typing. But both are the same thing. So that's our speed v. And the equivalent, so velocity, the vector equivalent of this, which is velocity, we just have the same equation, but now velocity v, and remember that for vectors we have a little arrow on top, so that is given by, now it's no longer the distance, so this s here was distance, now it's displacement, so it's the change in displacement over time. Okay, so what is displacement? Displacement is just the distance with direction. Okay, so let's maybe look at 2 examples to try and understand what we are talking about. So say for example someone is running a 200-meter track. So remember that the stadiums for Olympics, for example, are in a circle like that. So from here to there is half a full round, so that is 200 meters. So someone runs from here all the way over there, then the distance they've covered, which I called S, so the distance S would be the 200-meter race, whereas the displacement, as you can see, is different. So displacement has direction is from the starting point to the end point, and you draw a straight line. So my line is not as straight as it should be, but it's one straight line and it's directed towards the finish point. So this is where they start the race, and that's where they finish the race. And you can see that the length of the track is not necessarily 200 meters, it's smaller than that, and it's almost like a football pitch size, so about 160 meters, maybe let's say in the direction of motion, just for direction. So in the direction of motion, which in this case looks like east in my diagram. So we just say 160 meters east. So that's displacement. Okay, and we use a vector, so then we would write S is equals to 160 meters east. And also notice that sometimes, even though one has a non-zero distance, one can also at the same time have a zero displacement. So if we run the full 400 meters from here all the way around back to where we started, then the distance for that race is 400 meters, whereas the displacement is zero because we are back where we started. Okay, so it's just zero. Okay, so if we can just go back, now we have covered displacement and we have covered velocity, and now we want to, and also speed, we want to look at acceleration. Okay, so what is acceleration? So let's just write it down first. So acceleration is the rate of change in velocity. It's also a vector, so it's not the rate of change of speed, it's the rate of change of velocity. So then of course you can guess the equation. We use A for acceleration, it's a vector, so I need the arrow. So A is equals to delta V, which is a vector, over delta T, and you can see V is measured in meters per second and T is in a second. So combining these two, the unit for acceleration is meters per second square, or sometimes it's written as meters times second to the minus 2. Okay, so that's acceleration. And yeah, so if I may just show you the plan for today. So we have discussed displacement, we have spoken about speed and velocity, we've just introduced acceleration. So now what we would like to do is to study equations of motion, or sometimes called equations of kinematics, for constant acceleration. Okay, so we want to study acceleration which is constant. So when A is constant, so constant means both direction and magnitude. So for example, if a planet is rotating around another one, so where you have the sun and say that's planet Earth going around the sun, if this is going around at constant speed, it's not gonna give us constant velocity, because velocity is also direction. So when Earth is here, the direction is tangent. When the Earth is here, the direction is tangent. When the Earth is here, the direction is tangent. So you can see that there's a constant change in direction, so there is acceleration. And in fact, one gets centripetal or centrifugal acceleration, and that's just the gravitational force from Newton's law of universal gravitation. Okay, so um, uh, okay, so there's a force of attraction that acts, and it's responsible for the acceleration, because remember that this is equals to mg. So there is gravitational acceleration over there. Okay, so we are looking at where both direction and magnitude are constant, and this is only possible when something is traveling in a straight line and at constant acceleration. Okay, so uh, that's what we are interested in, and uh, for this we get what are called the equations of motion. Okay, so there are 4 equations of motion. I'm actually going to state them and then define the symbols. So just a reminder, we spoke about speed and we said we use v for speed. We had s or h for distance, and we had a for acceleration, we had t for time. So using these symbols, we differentiate between speed. So normally we would have initial speed, so we use small letter I for that, just to say it's the initial speed. We also have the final speed or final velocity, and then when we speak about direction, motion in the y direction, we use h. In the x direction, we use s. So that's for y and that's for x. Okay, and then acceleration, there's a notation. So when we have free falling bodies or something going towards earth, we normally use g for that, and g is known, it's 9.8 meters per square seconds. If you want to be more accurate, you can just say 9.81, and then t is always t. Okay, so depending if you can check, so here how many variables do we have? We've got 1, 2, 3, 4, because remember this is also a, and 5 with t. So with these 5, there are 4 equations of motion that help us to find any of the unknowns, and the equations of motion are the following. So we've got Vf equals Vi plus At, and remember that A can is substituted for G when we have a free falling body, or any motion under the influence of gravity only. And then we have another one, which is Vf squared equals Vi squared plus 2As. And then we also have S or H is equals to 1/2 Vf plus Vi multiplied by T. So you can see, just to remind you, this is what we called the average velocity, VAV AVG. So it's just S is equals to Vt, which is the case where normally one doesn't have acceleration, but because the speed is changing, we have final, we have initial, there is acceleration here, which is constant. When there's no acceleration at all, Vi equals Vf, so Vi equals Vf if a equals to 0, and what we see is this equation just becomes S is equals to Vt, because you will get V plus V, and that's 2V, it cancels the half, and you get S is equals to Vt. Okay, and then finally we have the equation of motion, which is S is equals to Vit plus 1/2 At squared. Okay, so if you check all of these equations, they only have 4 variables. So it's VI here, VF, A, and T. Here it's just okay. So here it's just VF, VI, A, and S. So here in the first equation of motion, we don't have S. In the second one, we don't have T. In the third one, I've already said we don't have A. In the final equation of motion, what we are missing is VF. So depending on what type of information you are looking for and what you are missing, you would then have to pick the appropriate equation of motion. Okay, so now we have also covered section 2.4 of the study guide, which is equations of kinematics or motion for constant acceleration. So all that is left now to do is to cover some applications and to do some questions. Okay, so just a reminder, in your book we are looking at sections 2.1 all the way up to 2.5. So 2.1, 2.2, 2.3, 2.4 and 2.5. Okay, so if there is 2.6 or anything else, that means it's not part of the syllabus, so we don't cover that. Okay, and so now what I would like to do, and a reminder also, this is on pages, so if you check your study guide, it's on page 40. We're looking at page 40, page 41 and page 42. So now we are going to go to page 42, and we are interested in looking at some examples. So let's look at example number 8 in the questions that we cover in lectures. So what do we have here? We've got a racer or a race driver that has made a pit stop to refuel. Okay, so the race driver has made a pit stop to refuel, and after refueling, so this is normally for your Formula 1 cars in a race, he leaves the pit area with an acceleration whose magnitude is 6 meters per second. After 4 seconds, he enters the main speedway. So yeah, this is a normal racetrack. And then at the same instant, another car on the speedway traveling with a constant speed of 70 meters per second overtakes and passes the entering car. And if the entering car maintains its acceleration, how much time is required for it to catch the other car? Okay, so I have already solved this problem, so my solution is over here, but let's just briefly discuss it. Okay, so what do we have? We need a new page, so let's open a new page. Okay, so we are looking at page, let me just double check, page 42, problem number 8. Okay, so let's relook at the problem. So we are told that we have a race car. So under the race car, so I'm going to separate the problem into two. I'll look at the race car before entering the pit. So this is before, entering the racetrack. So we are told that the driver makes a pit stop, so there's no information there, and then after refueling he leaves the pit area. So we know that the initial speed, which is VI, equals 0. Again, so before you even do anything with these equations, you need to choose the direction where you have positive. So I always choose positive to be the direction of motion. So direction of motion, because it simplifies the problem. You will get a lot of variables being positive and only a few being negative. So we know that the initial speed is 0, and then he leaves the pit area with an acceleration whose magnitude is 6. So acceleration in this case, because he's starting from 0, is accelerating the same direction. So A is equals to positive 6 meters per second square. If they said he is decelerating, then you would have a minus instead of a plus. Or if he's accelerating and the car slows down, then you would have a minus. Okay, because that's opposing the motion. And then after 4 seconds, So it takes him 4 seconds to accelerate at that rate. He enters the main speedway. So here, this is before he enters the main speedway. Okay, so before main speedway, this is what we have, and we are told that, so let's say after over here. So now we have after. Okay, at the same instant, another car on the speedway traveling with a constant speed. So let's call this car A. After, we have car B, and car B is traveling at V is equals to 70 meters per second, and it's constant. So that means the acceleration is 0, and we can just use S is equals to Vt. Okay, so what else are we told? It overtakes and passes the entering car. If the entering car maintains its acceleration, how much time is required to catch the other car? So this is important, and what we have is, at some instant here, car A is accelerating at 6 meters per second, and we want to know what speed car A is moving at. So to find the final speed for car A, which I've called VA, we need to use equations of motion. So here we have VI, we have A, we have T. The equation of motion, which doesn't have S, so there's no S over here, is VF, sorry, equals VI plus AT. And we are looking at car A. So VF is just, our VI is 0, our A is 0.6, and our time is 4. So then we just get 24 meters per second. So we know that the speed at which the car A enters the main speedway or the main track is 24 meters per second. At the same time, another car B is moving at VB is equals to 70 meters per second. So this one overtakes that one, and later on they meet again, and this one, so car B is still moving at 70 meters per second. We want to know how much time is taken from when they pass each other to where they meet. We can see that both of these cars are going to travel the same distance S, and we start the clock when they meet, so they both have the same time, so which I'm gonna call T. Okay, so from car B, what we learn is S is equals to Vt, and V is 70, so the distance is just 70 times T. For car A, what we learn is we are looking for S also, so S is equals to VAT plus 1/2 AT squared. Just a small mistake there, so let's make sure that we erase that and get our pen back. So 1/2 AT squared, and remember that the driver A maintains the acceleration A, which is 6 meters per second squared throughout the race or before they catch up. So here we know that S is equals to VA is just 24, we don't know the time, plus 1/2, the acceleration is 6, we don't know the time, T squared. So combining these two, we get 24T plus 3T squared. But we said that the distance S is equal to the distance S for both A and B. So equating these two equations, we have 70T equals this number, which is 24T plus 3T squared. So 3T squared plus 24T equals 70T. And simplifying this, we get 3T. So 70 taken to the other side is negative, and 24 minus 70 is 46. So let's just see, 2050, yes, 46. So minus 46, t equals to 0. There's a square here, so taking out a common factor of 3t, I'm left with t minus 46 over 3 equals 0. So then we get our final solutions. So there's two solutions. There's t equals to 0 or t equals 46 over 3 seconds. Okay, so which answer is the correct one? We're looking at when they catch up. This is when overtaking takes place. So at t is equals to 0, that's where car A is overtaken by car B. So that's not our solution. And our solution for catching up then would be after 6 over 3 seconds. Okay, so it's about 15.33. So t is equals to 15.33 seconds. Okay, what was the question? So the question is how much time is required for it to catch the other car, and that's the 43.33. Okay, so now we have looked at number 8. Now we are interested in number 7. Okay, so number 7, let's have a look. Okay, there's a small problem here. Okay, good. So we are looking at page 42, number 7. So page 42, number 7, what are we told? We are told that we have a log which is floating swiftly. Let me actually switch. So we have a log that is floating swiftly on moving water. A stone is dropped from rest from a 75-meter bridge and lands on the log as it passes under the bridge. If the log moves with constant speed of 5 meters per second, what is the horizontal distance between the log and the bridge when the stone is released? So here I've got the diagram. What we have is we have a bridge, and there's someone here at the bridge, and they drop a stone, and the height of the bridge is 75 meters. If they drop the stone, then we know that the initial speed for the stone is 0, and we have a log at the same time which is traveling through. So under the bridge there's some water, and the log is just traveling towards the right in this case, at 5 meters per second, which is constant. So for the log we can just use S is equals to Vt, whereas for the stone we have G, and I've chosen down as positive for my direction. And as soon as the stone hits the water, we are told that it hits the log. So it exactly hits the log. The height is 75, and we want to know what is this distance here that the log traveled to reach the stone. Okay, so let's have a look. So just to redraw the diagram, so there's our bridge. Under here there's water. We have a log over here, and at the bridge someone drops a stone. The height of the bridge H is 75 meters. Okay, and we said that the initial speed is 0. I've chosen down as positive for the log, and I've chosen towards the right as positive, or sorry, for the log is towards the right, and for the stone it's down. So we know G for the stone, it's positive, which is 9.8. So we need to find the time, because S is equals to Vt. We know the speed of the log. We just need the time to find the distance between the log and the bridge. I mean that the log traveled before it actually reached the stone. So here we have H, we have Vi, and we have G. We want T. There's no Vf, so the equation of motion that we are going to use for the stone, so this is for the stone, is I've called it H. So H is equals to Vit plus 1/2 G t squared. Okay, so vi is 0, so that term is just 0. We are looking for t, so we need to multiply or divide by half g. So if we do that, we find t squared equals h, the 2 goes on top over g, so that means t is equals to the square root of 2h over g. Substituting the values, we find t is equals to square root 2h is 75 and g is 9.8. So if we now calculate this, what one will find is, let me just check, 3.91 seconds. Okay, so one should find 3.91 seconds. So that's the time it took for the stone to reach the log, but that's the same time that the log took to go from here to reach the stone. Okay, so that's the same time t. So then we learn s is equals to vt. V is 5 and t we've just calculated, we said 3.91. So multiplying these two, one finds that s is just 19, not 19, yeah, so s is 19.56 meters. Okay, so that solves question number 7. Okay, so now which question? So now we are looking at number 6. Okay, so let's just switch and make sure that we shift the book so that you can see which question we are doing. So we're looking at number 6, and number 6 tells us we have two balls which are dropped to the ground from different heights. This is page 41, and one is dropped 1.5 seconds after the other, and they both strike the ground at the same time, which is 5 seconds after the first one is dropped. Calculate from which height was each ball dropped. So that's another question. It's not too difficult. So we are looking at page 41, number 6. Okay, so page 41, number 6, what do we have? There's our ground. We have a stone, let's call it stone A, and it's dropped at some height. Let's call it height up for large. Another stone is dropped at a smaller height, which we'll call h down for small. Let's call that one B. So we will choose down as positive, which is the direction of motion. That means our G is positive 9.8 meters per second squared. These are dropped, so VI for A is equals to 0 and VI for B is equals to 0. We know that it takes 5 seconds for the first ball, which is the ball at the higher height. So then TA is equals to 5 seconds. But for B, B is released 1.5 seconds later, so TB takes 1.5 seconds less. So it's 5 minus 1.5, which is 3.5 seconds. Okay, so the time it takes for B to reach the ground. And we'd like to find h down and h up, so the height of B and the height of A. So the height of A is given by VI t plus 1/2 g t squared, because we don't have the final speeds for both of them. So then VI is 0, so that term just dies. So then we just have 1/2 9.8, and t for A is 5 seconds squared. So multiplying these out, you get HA is 122.5 meters. Okay, what about B? So for B, HB is the same equation. We also don't have the final speed, so VIT plus 1/2 t squared times G. So TB here I should have written TA for the A, and here VI is 0, so we just substitute. We have 1/2. The time for B is 3.5, so 3.5 squared times 9.8. Multiplying these two out, we find HB is equals to, let me just check, 60.8 0, so that's a 0, 60.025 meters. Okay, so those are the heights of the two objects, or the two balls. Okay, so that's number 6. Now we will skip number 5 and go to number 4. So number 4 says a train takes 25 seconds to pass through a town with constant speed. So let's just stop there and record the information. I'm trying to get a new page. Okay, so let's remove that. So new page. So we are on page 41. We're looking at problem number 4. Okay, so a train goes through town. So through town, the information that is given is that it travels at constant speed. So constant speed means we can use S is equals to Vt. And let me just check. It takes 25 seconds to pass through town at a constant speed of 16 meters per second. So T is equals to 25 seconds, and V is equals to 16 meters per second. We choose positive as the direction of motion. So direction of motion. And we can easily see that we can find the distance for through town using S is equals to Vt. Okay, so let's continue reading. And then we are also told after leaving the town, the train accelerates at 0.33 to reach a final speed of 35 meters per second. So after leaving town, so let's just say after town, accelerates, so A is positive, A is equals to plus 0.33 meters per square second. It's positive because also the final speed is larger than the initial speed, so the final speed is 35 meters per second. If before it goes after town it was moving at 16, that means the initial speed was just 16 meters per second, not second square. So let's just remove that. Okay, so we're looking for the distance. So the question is how far did the train travel during this time? Okay, so to calculate how far the train traveled, we are looking for the distance S. So you can see that there's two parts. So let's call this S1 and call this one S2. So then S1 is Vt, which is 16 times 25, which is just 400 meters. Okay, so that's S1. Then S2 is equals to Vit plus 1/2. Oh, we don't have T, so the equation we are going to use is Vf squared equals Vi squared plus 2As, and we're looking for S, so let's take Vi to the other side and divide by 2A, so we get Vf squared minus Vi squared over 2A equals the S that we are looking for. So S is equals to Vf is 35, so 35 squared minus 16 squared over 2 times 0.33. Okay, so if you plug those in, what you find is S2. So let's just make sure that that is S2. S2 is 1468.2 meters. So then the total distance that the train travels, S is equals to, so S total is equals to S1 plus S2, which is just, if you add this distance with 400, you get 1868.2 meters. Okay, so that's part A of the problem. So we have solved part A. Part B, we are being asked what is the train's average speed during the trip. So what we need to do is we need to first find the average speed through town, find the average speed after town, and then the average speed for both of these trips. Okay, so for through town, the average speed is just v. So v is equals to v average because it's a constant speed, so which is just 16 meters per second. And then after town, the average speed is found by adding the final and the initial and dividing by 2. So v average is 1/2 vf plus vi. The same way that if you've got two people, one weighing 100 kilograms, another weighing 50, you want to know their average mass. Maybe these are rugby players in the same team. Then you would just add 100 to 50 and divide by 2 to get 75. So it's the same concept. We take the initial speed, add the final speed, divide by 2. That's the average speed for the trip. So if you do that, what you will find is the average speed is just 25.5 meters per second. So VF, just remember, is 35, VI is 16. So adding these two, dividing by 2, you get 25 meters per second. So now we need the average for the whole trip, and the average for the whole trip is just adding the average for trip 1 to the average for trip 2, divide by 2. So V average in total is just V1 average plus V2 average over 2. So V1 average is this here, so that's just 16, and then the average speed for the second trip is this one here, so that's 25.5 over 2. Then our average speed for the whole trip is just if you add those two and divide by 2, which is 20.75 meters per second. Okay, so that completes question 4, and then now I would like to look at one more problem from the problems that we cover in lectures, and that's question 3. So for question 3, we have Carl Lewis, who's an Olympic runner, who set a world record for the 100-meter run with a time of 9.86. So this guy was very quick. He covered 100 meters in 9.86, and then after reaching the finish line, Lewis walked directly back to his starting point in 90.9 seconds. And what we want to know is to calculate the average speed for the 200 meters and to calculate the magnitude of his average velocity for the same 200 meters. Okay, so let's just open a new page. So what we want to do is to realize, so we are looking at page 41, number 3. Okay, so what we have here is we have a runner, Carl Lewis. He covers 100 meters, so the distance here is 100 meters. So first he runs the 100 meters in a race against other people, and it takes him 9.86 seconds. Okay, so that's the time it takes him, and that's a world record. So we'll just say time 1 for the forward run. And then afterwards he's tired and he walks back. So now he walks back and it takes him time 2, which is 90.9 seconds to cover the same distance. So now you can see that for the forward trip, which is over there, let's use blue again. So for the forward trip, we have S is equals to V average for this trip. So we want the average speed for this trip. So S is Vt because we are using average speed. So average times T. If you're not happy with this, just think of this as 1/2 Vi plus Vf times T. So 1/2 Vi and Vf is my average speed. So even though the racer will be accelerating, we don't worry about that. We just want the average speed, which is given by this equation of motion. So for this, I'm going to choose positive to be the direction of motion, well, not direction of motion, but positive to be for the run. That means going back, I have a negative. Okay, so we learn that V average equals S over T, which is 100 meters over 9.86 seconds. And if you calculate that, what you will find is his average speed is 10.14 meters per second. Average velocity for that trip, the same trip has direction, so it's gonna be 10.14 meters per second east. Okay, and then now he goes back and he walks. So for walking back, we have S is equals to V average again, so that's the red trip going back, times T, and that means the average speed is equals to S over T, and S is the same, so 100 meters, and the time it takes now is 90.9 seconds. If you multiply those two or divide those two, what you will find is the final answer for that duration is 1.10 meters per second, and that means the average velocity for the second trip is just 1.10 meters per second west. Okay, so then the question is calculate the magnitude of the average speed for the 200 meters. So the first part, we are interested in the average speed. So then remember that the average speed is just the speed for the one trip, which is forward, plus the speed for going back divided by 2. So average speed for the whole trip is just equal to the blue speed is over here, so V, not velocity speed, so V average here, and then I need to add the red speed, so V average from here and divide by 2. So it's the sum of those two over 2. If I do that, what I find is I have 10.14, so 10.14 plus 1.1, so 1.10 over 2. Then I learned that for the whole 200 meters, the average is just, let me just see. Okay, so I haven't calculated it here. I'm just gonna look for a calculator. Okay, so whilst I'm looking for my calculator, I just want to say that there's another way of finding this average speed. You can just say for the whole trip, the average speed is the total distance over the total time. Okay, so the total distance was 200 meters, and the total time is okay, so I'm being helped with the calculator. Okay, so there we go. Okay, cool, thanks. So what we have is we want 10.14, and to that we add 1.1, and we want to divide by 2. So if I divide by 2, I get 5.62. So my answer is 5.62 meters per second. And I just said there's another way, so you can take the whole distance divided by the total time, which is 90.9 plus 9.86. So just to check that our answer corresponds, so what we have now is we want to add 90.9 to 9.86. Okay, so that's 100 point. So let's just record that number. That's 100.76 seconds. So what I want to do now is take 200 and divide by our 100.76. Okay, so they don't give the same answer. That's odd. We get 1.98. Okay, I will check this, and then in the next lecture I will just say which, but I think this is the correct answer and what was the problem with the other one. Okay, so now we go to the second part of the problem, which is part B. We want the magnitude of the average velocity, and then we are done for this lecture. So we want the magnitude of the average velocity. So the magnitude of the average velocity is not very difficult to find. So just remember that now we have directions. Just a reminder that we had for the forward trip, which was where you were sprinting, v average velocity was 10.1 let's just 10.14 meters per second, and this was east. And then the return trip, the average velocity was 1.10 meters per second, and this is west. Okay, so if now I want the average velocity for the whole trip, so for the whole trip I just need to add for the forward trip the average velocity to the average velocity for the return trip and divide by 2. So if I add those two and divide by 2, just remember that these are vectors, so east is what we said was positive, that means west is negative. So this is actually 10.14. It's a plus minus 1.10 over 2. So if I add those two in that fashion, what I find is my average velocity for the whole trip is, so I want 10.14, and to subtract 1.10 for this trip, which is 9.04, and to divide by 2, and we have 4. Okay, so we have 4 point, let's just double check, 4.52. Okay, so it's 4.52, and it's a plus meters per second, which means it's 4.52 meters per second east. Okay, so that's the final answer. And actually I've just realized what's wrong with the other equation, because even here remember that average velocity would be given by the displacement and not the distance over the total time. The displacement in this case is 0. So if the displacement is 0, that means the average velocity is 0. But that's not the case, because the person ran at a different speed going forward and ran at a slower pace coming back. So this formula gives us the wrong answer in this case. So that is why when we tried to calculate earlier over here, we got the wrong answer. Okay, so you need to use the speeds themselves to get the correct answer. Okay, so that solves why this gave us a wrong answer. Okay, so that's the end of the lecture. I would encourage that you do your tutorials, and then I will send my solutions via Blackboard, and you can look them up. Okay, thanks. That's the end of this section.